Welcome to Part 6B, part of Week 6. In 6A, we learned how to summarize data with aggregate functions, group by and halving. But now we're going to take a significant step forward in SQL complexity by learning subqueries. A subquery is a query nested inside another query. It's one of the most powerful tools in SQL. And by the end of this part, you'll be able to write queries that answer multi-step analytical questions in a single SQL statement. What are our learning objectives for this portion? We have 6. First, you will understand the fundamental concept of a subquery, including how inner and outer queries interact. Second, you will write scalar subqueries that return a single value for use in a comparison. Third, you will learn how to use subqueries with the in, exists, any, and all operators, each of which serves a different purpose. And fourth, you will learn the critical distinction between correlated and non-correlated subqueries, which affects both how they execute and their performance characteristics. Fifth, you will apply subqueries not just in where clauses, but also in select and from clauses, which opens up some entirely new analytical patterns. And finally, sixth, you will develop judgment about when to use a subquery versus a join. Sometimes each will give you identical results. So some problems can be solved either way. This section introduces the core concept of a subquery. Think of subqueries as the ability to ask a question that depends on the answer to another question, all within a single statement. In healthcare analytics, this comes up frequently. For example, show me the patients whose blood pressure is above the average. It requires first calculating the average. That's one query, and then filtering the patients against it, a second query. Subqueries let you combine both steps. So what is a subquery? It's a simple SQL query nested inside another SQL query. The outer query is sometimes called the main query or parent query, and the inner query is called the subquery, inner query, or nested query. The key execution principle is that the inner query runs first. It produces a result, and that result is then used in the outer query. So subqueries are always enclosed in parentheses. That's how you can tell it's a subquery. This is how Postgres knows where the subquery begins and ends. They can be placed in several different parts of a SQL statement. In the where clause for filtering, in the select clause for computed columns, in the from clause for a derived table, or in the halving clause for filtering groups. This is very complicated, so let's take that one more time. Subqueries are always enclosed in parentheses. That's the syntax. They can be placed in several different parts of a SQL statement. It can be in the where clause for filtering, in the select clause for computed columns, in the from clause for a derived table, or in the halving clause for filtering groups. The diagram on this slide illustrates the data flow. The inner query at the bottom executes first. Its result bubbles up, and the outer query consumes that result to produce the final output. Keep this mental model in mind as we work through some examples. Let's look at the general syntax and the execution flow. The outer query has a standard select, from, and where structure. Inside the where clause, after a comparison operator, we have a parenthesized select statement. That parenthesized statement is the subquery. The 3-step execution flow is straightforward. In step 1, the inner query executes. It executes first and independently and produces the result. Step 2, that result is passed back to the outer query. And in step 3, the outer query uses this result to complete its filtering or computation. So there are 3 key rules to remember. Subqueries must always be enclosed in parentheses. That's the syntax. And they typically return one column when used in where or having, and they can be nested multiple levels deep, meaning you can have a subquery inside a subquery inside a subquery, although readability suffers quickly when you start trying to do this, to chain them, daisy chain them. So let's look at the types of subqueries. Here are the 6 different subtypes. Take a moment to familiarize yourself with each of these, because we will cover each type in the coming examples and slides. Now, a scalar subquery, what is a scalar? It means a simple single value. It returns just one value, as opposed to a row or a column. You use it with comparison operators like equals, or greater than, or less than. Now, column or list subquery returns a single column with multiple rows, like a list of patient IDs, and you will use it in, any, or all. A row subquery returns a single row with multiple columns, and it's used for row-level comparisons. Now, the next level is a table subquery, also called a derived table. It returns a full result set, like a table, and is used in the from clause as if it were a temporary table. The last 2 rows of our examples in this slide describe a behavioral distinction rather than a really structural one. A non-correlated subquery is independent and runs once, whereas a correlated subquery references the outer query and runs once per row of the outer query. We'll spend a significant amount of time during this lecture looking at the distinction between these approaches, because it affects both how you write your queries and also how efficiently they perform. All right, the simplest case, the scalar subquery, returns just a single value, not a row, not a column, a single value. This makes it suitable for use with standard comparison operators like equal or less than or greater than. In this example, we're trying to find the patients that are older than the average age for the practice. What does the inner query do? The inner query extracts year from age from the date of birth to convert each patient's date of birth into a numeric age in years. Now, it's important for you to understand this. Extract year from age is a built-in Postgres function that allows you to not have to write a lot of code to figure out how to get the age from a birthday. This is built in. Then the average calculates the mean age across all the patients in the practice. So the outer query uses that same extract age pattern, the built-in function, and then it compares each patient's age against that average that we got from the inner query, returning only those who are older. So the concept is the key takeaway. The inner query computes a single value. The outer query uses it as the filter threshold to find records that meet your criteria. So if a scalar subquery accidentally returns more than one row, Postgres will throw you an error. It'll crash. Make sure your subquery logic guarantees a single return value when using it with a standard comparison operator. Okay, what about scalar subqueries examples in healthcare? Here's a practical example. We want to find all encounters where the patient's systolic blood pressure was above the clinic-wide average. Okay, so the inner query calculates the average systolic blood pressure from all the encounters, filtering out the nulls to get an accurate mean. The outer query joins encounters with the patients to get the patient names. That's a join. And filters to only those encounters where the systolic blood pressure exceeds the average that we got in the inner query. So notice the null handling in the inner query with the where blood pressure systolic is not null. This is important because as we learned in the first part of week 6, average ignores nulls. But being explicit about it using the is not null is safer. It's not required. The results would be the same if you hadn't done that because the average function knows to ignore the nulls, but it's always safer to be explicit. So the result is going to be ordered by blood pressure descending, so the highest readings appear first on your list. In the clinical context, this query could feed a dashboard that flags patients with uncontrolled hypertension that need follow-up in the clinic. Give your providers a list of patients that need more attention. We'll be discussing this a little bit more in the fourth part of this week. How about subqueries with in? What does the in operator do? It checks whether a value matches a value in a list that in this case is returned by a subquery. Think of it as a shortcut for writing multiple OR conditions. The in list substitutes for multiple ORs. So look at this example. It's going to find all the patients who have been diagnosed with type 2 diabetes. How do we find all the patients with type 2 diabetes? You have to know a little bit about the ICD-10 code structure to know that. But there are lots of different diabetes type 2 codes, but they all start with E11. And in PostgreSQL, we have the like operator. So if we put quote E11%, end quote, that wildcard percent will find all the ICD-10 codes that start with the 3 characters E11, and that's going to get you all the type 2 diabetics. So that was an intentional design of the ICD-10 code structure to make it easier to do code searches and do research to find patients with similar conditions, in this case diabetes. Now the inner query in this example will find all patient IDs that appear in encounters linked to a diabetic diagnosis, type 2. The outer query then returns the names of patients whose IDs are in that list. So now notice carefully that we use the distinct keyword on the outer select. Without it, if a patient had multiple encounters, and with a diabetes diagnosis as part of that encounter, they'd appear on your list multiple times. We usually don't want that. So the distinct ensures that each patient appears only once. The in operator is intuitive. It's readable, which makes it a popular choice. However, for a very large result set, it can be slower than exists, and we will cover that next. Subqueries with not in. Not in is the opposite of in. It excludes rows where the value matches anything in the subquery's results. So let's look at this example. This is to find the patients who had 0 encounters during the year 2025, which might indicate the patients are lost to follow-up, at least have not been seen recently. However, there's a critical warning on this slide that you need to understand. It's at the bottom of the slide there. If the subquery returns any null values in its result set, not in will return 0 rows. And this is a well-known SQL gotcha. The reason is that comparing any value to null with not in produces unknown, not true. So SQL only returns rows where the condition is true. So what is the practical solution? Ensure your subquery cannot return nulls by adding a where column is not null as a filter, or use not exists instead, which handles null safely. We cover exists in this next slide. Exists works fundamentally differently from in. Instead of comparing values, it just simply checks whether the subquery returns any rows at all. If the subquery returns 1 or more rows, exists evaluates to true. If it returns no rows, it'll evaluate to false. The example finds patients who have at least 1 lab result. The subquery correlates with the outer query through the patient ID equals the lab result patient ID equals the patient ID. For each patient in the outer query, the inner query checks if any lab results exist for that patient. Now notice that this weird thing called select one which is inside the exists subquery. This is a convention that's commonly used. Since exists only cares about whether rows exist, not what their values are, not the values they contain, we select the literal value 1. You could also use a select star or select anything, and the result would be the same. But select 1 is simply the shortcut and a standard practice because it clearly communicates that we only care about the fact that a row exists, not the data within it. So exist is more efficient than in for large data sets because it can stop searching once it finds the first matching row, rather than bundling a complete list of all matching values. This comparison table will help you to choose between exists versus the in your queries, which to use when. The most important difference is null handling. Not in is problematic when nulls are present, as we discussed in the previous slide. Not exist handles nulls safely because it operates on row existence, not on value comparisons. Now for performance, exist is generally faster, especially with large data sets because it short circuits after finding the first match. In must evaluate the complete subquery result set before proceeding. But for readability, in is simpler and more intuitive for straightforward list matching. Exist is better when the logic involves correlation between the inner and outer queries. The rule of thumb at the bottom summarizes it well. Use in for small results sets where readability matters, and use exists for large or correlated queries where performance and null safety matter. So here's the difference between the correlated and non-correlated, how subqueries relate to the outer query. This is one of the most important conceptual distinctions in subquery knowledge. Whether a subquery is correlated or non-correlated determine how it executes, how it performs, and how you should think about it when you're writing your code. What's a non-correlated or independent subquery? Non-correlated is completely independent of the outer query. It runs once, produces a result, and that result is reused for every row the outer query evaluates. There's no reference to any column from the outer query inside the subquery. The example here finds the most expensive insurance claim. The inner query there computes max of total charge from the entire insurance claim table. This runs once, returns a number. The outer query then filters for claims matching that exact amount. So how does this actually execute? The execution flow is clean and efficient. The inner query runs once, returns that maximum value for the charge, and then the outer query uses that value as a constant filter to identify the cases where a patient had the maximum charge. This is the simplest and most performant type of subquery. How about correlated subqueries? A correlated subquery is different. In a fundamental way, it references one or more columns from the outer query. This means the inner query cannot run independently. It must run once for each row that the outer query processes. So, look at this example. It finds the patients whose BMI exceeds the average BMI for their gender. For their gender, that's the key. So we can't just find that answer once and apply it to the whole rest of the table. The inner query references patient.gender from the outer query. So for each row in the outer query, the inner query calculates the average BMI for that patient's gender, and then the comparison happens. So it's going to every row, it's going to recalculate the average BMI. Not necessarily very efficient, but it's shorthand, easy to write the code. The inner query calculates the average BMI for that gender, and then the comparisons happen. If the outer query processes encounters a male patient, then the inner query will calculate the average BMI for the males. If it encounters a female patient, then that inner query will calculate the average BMI for the females. This is why correlated subquery is executed repeatedly rather than just once. The note at the bottom of the slide highlights the telltale sign. P.gender inside the inner query comes from the outer query's patient table, aliased as P for patient. The inner query uses P2 and E2 as separate aliases to avoid confusion with the outer query's tables. So correlated subqueries are more powerful but slower due to the repeated execution of the inner query's code. And for large tables, the performance impact can be significant, so use them judiciously. All right, this slide demonstrates what is probably the most common use case for correlated subqueries in a healthcare example. Finding the most recent record for each patient. This pattern appears constantly in clinical analytics. You might need the most recent lab result, the most recent encounter, the most recent blood pressure reading, or the most recent medication list. What does the inner query do? The inner query finds the maximum encounter date for that specific patient being evaluated. In the outer query, using E2.patientID equals E.patientID as the correlation, for each encounter in the outer query, it checks whether the encounter's date matches the maximum date for that patient. What's the most recent visit? When were they seen last? The result will be only one row per patient, their most recent encounter, showing the most recent encounter date and the chief complaint. This is invaluable for building patient summaries or clinical dashboards and used a lot in quality measuring calculations or evaluations or analytics. Very often you'll need the most recent for your analytics. Now in part 6D coming up, you will see this exact pattern used to find the most recent blood pressure reading for some of the HEDIS quality measures. Now, up to this point, we've been placing subqueries in the where clause, but subqueries can also go in the select clause, adding a computed column to each row of your result. Look at this example. It selects provider information, but adds an encounter count column. The subquery in the select clause counts encounters for each provider. Because it references p.providerID from the outer query, it is a correlated subquery that has to execute for each provider row. This pattern is useful when you want to enrich existing data with computed metrics without restructuring your query using the group by. The result shows each provider's name, specialty, and then their total encounter count, ordering from the busiest to the least busy, in just those few lines of code. One thing to keep in mind, since this is a correlated subquery running per row, it can be slow if you have large provider tables. If you're concerned about the performance, you could rewrite this using a join with a grouped subquery. But for moderate size data sets and readability, the select subqueries approach is perfectly fine. Now, when a subquery appears in the from clause, it acts as a temporary table, often called a derived table. The outer query treats the subquery results as if it were a regular table and can select from it and filter it and aggregate it further. The critical rule is that a derived table must have an alias. In this example, the alias is visit counts. Without the alias, Postgres will throw a syntax error. This example answers the question, what's the average number of encounters per patient? What does this require? It requires a two-step aggregation. First, count encounters per patient. You see that in the group by patient ID. Then, average those counts. You cannot do average count star directly in SQL. The derived table pattern solves this elegantly for you by computing the per patient counts as a temporary table, and then the outer query averages over that temporary table. This is a very common pattern in healthcare analytics. Anytime you need to aggregate an aggregation, such as average counts or maximum of sums or count of averages, you likely use a derived table called a CTE. Subqueries can also be used inside a having clause. In this example, we find providers whose encounter count is above the average encounter count across all of the providers. So look at it carefully, go through it. This is a multi-level query. The having clause contains a subquery that itself contains a derived table. So let me walk through the layers. It gets deep. The innermost query counts the encounters per provider. That feeds into a derived table, a temporary table, which has an alias. The middle query calculates the average of those counts. And then finally, the outer query groups encounters by provider and keeps only those whose count exceeds the average. This is pretty complex, but it demonstrates a real analytical need. You identify the above average performers. In healthcare, this could be feed into provider productivity reports or help with workload balancing decisions. Any and all are less commonly used than the in or exists, but they serve specific purposes. Both are used with comparison operators and in subqueries. Any returns a true value if the condition holds for at least one value in the subquery result. Let's look at this example. First example finds claims with a total charge greater than any Medicare claim. This means greater than the smallest Medicare claim, because if your charge beats even one Medicare charge, that condition will be satisfied. All returns true only if the condition holds for every value in the subquery result. The second example finds claims greater than all Medicare claims. This means greater than the largest Medicare claim, because your charge must beat every single one. So, the practical difference is significant. Greater than any is a low bar, essentially greater than the minimum, but greater than all is a high bar, essentially greater than the maximum. So you need to understand that distinction. This prevents logical errors in your coding, in your queries. All right, let's talk about nested subqueries, a multi-level query. Subqueries can be nested inside other subqueries, creating multiple levels of depth. Look at this example. It has 4 levels of nesting to answer the question, which patients have a primary care provider who has an above average encounter count? So working from the inside out, what does the innermost query perform? It counts the encounters per provider. Look at it. And that feeds into average to calculate the average provider encounter count. The next level finds the provider IDs where the count exceeds that average. Then the next level filters to just those providers, and the outermost query finds the patients assigned to those providers. Now, a word of caution. While this works, deeply nested subqueries are difficult to read. They're hard to debug. They're very difficult to maintain. In practice, CTEs, or common table expressions, written with the with keyword, provide a much more readable alternative. Common table expressions, or CTEs, are an advanced topic. that may be covered later in this course if we have time, but know that they exist as a cleaner way to express the same kind of multi-step logic. All right, let's try to distinguish between the appropriate use of the subqueries versus joins, because they can give you equivalent results. This is a decision-making slide that will help you choose the right approach. Many SQL problems can be solved with either a subquery or a join, so understanding the trade-offs can be important. You want to use subqueries when you need to filter by an aggregated value, like to find the records above the average. Now, joins cannot directly do that. Use joins when you need to combine columns from multiple tables. Subqueries in where only filter. They cannot add columns. So, for an existence check, both work. Exist subqueries and join with the distinct clause can produce the same result, but exists is typically more efficient. So for derived data sets, from subqueries and common table expressions are both viable options. Either one will work. Either one will suffice. Now for readability, it depends on the complexity. A simple list matching is clear with the in clause. Complex multi-table column combinations are clear with joins. And for performance, joins are generally much faster, especially for large data sets. But it's not always the case. So what is the key takeaway? It's pragmatic. Many subqueries can be rewritten as joins and vice versa. Choose based on which approach makes your query more readable and maintainable in your specific situation. Look at this side-by-side comparison of two sets of codes. Both queries answer the same question: find the patients diagnosed with type 2 diabetes. The subquery version uses where the patient ID is in with a subquery, whereas the join version uses explicit joins between the patients, encounters, and diagnoses by using the distinct clause keyword. Both produce identical results. The subquery version is arguably more readable for this particular problem because it clearly separates the find the diabetic patient's IDs logic from the display patient names logic. The join version is more direct and may perform better on large data sets. So as you write more SQL, you will develop an intuition for which approach feels more natural for different situations. Sometimes there's not an absolute correct answer. What matters is that your query is correct, that it functions properly, and that it's readable and performs acceptably. All right, we're coming to the end here. What I want you to do now is to think about 5 specific examples. See if you can't write the code to execute these use cases. Let's look at problem 1 here. Use a scalar subquery to compare the BMI against the overall average. So how would you do that? In problem 2 here, you want to list all the providers who have never prescribed any medications. So in order to do that, you're going to have to use a not exists, which is a little bit more complex. This is going to test your understanding of correlated subqueries and that exists operator. Problem 3, find the most common diagnosis for each encounter type, may require a correlated subquery or maybe even a derived table to find the most common diagnoses per encounter type. How about problem 4? List the patients who had more encounters than the average patient. How would you do that? Well, you're going to have to compare the per patient encounter count against the average, which would be an inner query, a subquery with aggregation. And the 5th test case combines a subquery to find the busiest provider with another query to find their prescriptions. The little warning at the bottom encourages you to think about your approach before writing your code. For each problem, ask yourself, is a subquery or join more appropriate? Should this be correlated or non-correlated? Where should this subquery go? In the where, the from, or select? So what have we learned in this session? Let's summarize the 6 points that we started with. First, subqueries allow for complex multi-step logic within a single SQL statement, and they are essential for problems that require intermediate calculations and comparisons. 2. Scalar subqueries return one value only, and they work with comparison operators. Column subqueries return lists and work with the in, any, and all clauses. Third, the distinction between non-correlated and correlated subqueries is fundamental. Remember, non-correlated run once and are fast. Correlated run once per row, but are more powerful, but they're slow. 4. Exists is the safest and most efficient option for existence checks, especially with large data sets and when nulls could be present. 5th, derived tables in the from clause enable multi-step aggregations that cannot be done in a single group by clause. 6th, subqueries and joins are often interchangeable, so choose based on readability or performance or the specific requirements of the problem you're addressing. So the next part we're going to have, the third part of this week, is on indexing and query optimization, where we learn how to make all of these queries run a little bit faster.